Welcome to qnawire.
Hi, so in this case, what we are going to look at is the following reaction, the step one of a step two-step reaction. We're going to have CH4 in gas phase plus water in gas phase. That is going to produce CO in gas phase plus stream of hydrogen as a gas. We're told that the change of entropy for this reaction is equal to 214.7 joule per Kelvin, and we need to calculate delta H and delta G. So for the calculation for delta H, remember that delta H is equal to the sum of the delta H of formation of products minus the sum of the delta H of formation of reactants. And we need to multiply each of them by their stoichiometric coefficient. So what this is going to look like is that it will be delta H of formation for CO as a gas plus 3 times the delta H of formation of hydrogen as a gas minus delta H of formation for CH4 as a gas minus delta H of formation for water as a gas. Now, since I don't have access to the table of thermodynamic data that is given to you, I will employ Overby Chang book of chemistry, 13th edition, in the second appendix. So that's where the values that I'm going to be given are going to come from. So you can verify if they match up to the ones that are provided to you. Otherwise, you can follow the procedure and just substitute the values. So in the case for CO, in the gas phase, the value is minus 110 kilojoules, 0.5 kilojoules per mole. Remember that the mole is going to cancel out with the 1 mole that we had multiply over here. Plus 3 times for hydrogen. In the case for hydrogen, this is equal to 0 because it's a substance in its standard state. Now the formation for CH4 is equal to minus 74.85. Again, kilojoules per mole. And finally, for water, we have minus 241.8. Remember to always verify that you're employing the correct value in the correct phase. So the value for delta H for this reaction will be equal to 206.65 kilojoules. Now, we're provided with the value for delta S, so we can calculate delta G for the reaction as follows. Delta G for the reaction is equal to delta H minus T delta S. So this is 206.65. We are considering the temperature to be 298 Kelvin. 65 kilojoules minus 298 Kelvin times 214.7 joules per Kelvin. So, in order to sum both of these quantities correctly, we need to transform the delta H into joules. So this would be 206,650 joules. And over here, Kelvin and Kelvin are going to cancel out. So the delta G for this reaction is equal to 142,669.4 joules. Or, which is the same, 142.669.4 kilojoules. So the reaction is not spontaneous. At 298 Kelvin. So now the question is, at what temperature does the step 1 starts to become spontaneous? And for this, we're going to assume that delta H and delta S are not functions of temperature. They are going to be constant for all of the procedure. So for a reaction to be spontaneous, we need delta G to be lower than 0. So let's equate delta G for the reaction to 0, and this needs to be equal to delta H minus T delta S. That means that the temperature at which the reaction starts to become spontaneous will be equal to delta H divided by delta S. Oops. So this temperature corresponds to, again, 206,650 joules divided by 214.7 joules over Kelvin. And this is equal to 962.5 Kelvin. At this temperature, the reaction starts to become spontaneous. And as you can see, we're increasing the temperature, so at temperatures larger or equal than 962.5 Kelvin, the reaction is spontaneous. And that will be all. Thank you very much and have a good one.